How do you take a photo of something 6,500 light years away? What makes us see so many different colors in this beautiful golden pheasant? And this, we all take it for granted, but punch a few buttons and you're suddenly able to talk to someone 10,000 kilometers away without a physical connection. How is that possible? Well, the answer to all those seemingly unrelated questions is actually the same: electromagnetic waves. So let's understand what they are by breaking down the relevant study design dot point, having a go at a practice exam or SAC-style question, and leaving absolutely zero gaps in our understanding. Alright, so we are needed to describe light as a transverse electromagnetic wave which is produced by the acceleration of charges, which in turn produces changing electric fields and associated changing magnetic fields. That is a mouthful. So let's just start by breaking down the parts of this that we are already familiar with: electric fields and magnetic fields. We know that any electric charge exerts an electric force on other charges in a region around it, a region that we call an electric field, which has an associated magnitude and direction. Now, since that magnitude approaches but never really hits zero, we also know that these fields extend to infinity, meaning that there's an electric field that is spread over the entire universe. Likewise, for any object that is a magnet or acts like one, we have a region surrounding it in which any moving charge experiences a force. A region, again with a magnitude and direction, called a magnetic field. This also extends to infinity, leading to a magnetic field permeating the entire universe. Okay, cool. Let's now consider the acceleration of charges by looking at the most common example of an electric charge. Now, if an electron vibrates or transitions to a different atomic energy level, what happens is that it creates a wave in that electric field we just talked about that fills the entire universe. And what I mean by a wave in the field is repetitive fluctuations in both the field's magnitude and its direction, fluctuations that move through the field and, as such, travel through space. Such an electric wave, characterized by changing electric fields, happens to be generated not only by the acceleration of an electron, but of any electric charge in general. But that's not the only thing that's generated, because it turns out that electric waves have a sibling of sorts that they just cannot exist without: magnetic waves. That is, fluctuations in the magnitude and direction of that all-permeating magnetic field that travel through space. We've studied many concepts in physics so far, such as Faraday's law and the right-hand grip rule for a conductor, all of which point towards a relationship or an interlinkage between electric and magnetic fields. At the most fundamental level, what this means is that the production of an electric wave also creates a magnetic wave at the same time. And magnetic waves also create electric waves. So whenever you have an electric wave being made, it will always initiate a magnetic wave, and they will both keep generating each other to form a self-propagating pair of waves, which can thus travel forever and needs no physical medium to travel through. Their direction of oscillation is perpendicular to each other and to their direction of travel, which makes them transverse waves. These two interlinked waves form from the acceleration of any charge and are referred to as electromagnetic waves. Let there be light, because that is exactly what light is: electromagnetic waves. And if we consider all possible wavelengths of electromagnetic waves arranged from shortest to longest, we get an entire electromagnetic spectrum that allows us to categorize these waves according to their wavelength and frequency. The type with the longest wavelength is radio waves, while those with the shortest are called gamma waves, with each having a multitude of applications in both science and society. Feel free to pause the video and have a read of their uses. And there you go, that's the entire dot point covered. But before we finish off, let's just quickly apply our knowledge to this 3-mark question that asks us to describe the production of an electromagnetic wave and to give one example of its use. We'll aim to have 3 key points, 1 for each mark, and we'll dedicate 2 marks to the description and 1 mark to the example. Okay, starting off from the foundation. When a charge accelerates, such as an electron transitioning to a lower atomic energy level, an electric wave is generated. Let's now build on that and finish our description. This electric wave generates a perpendicularly oscillating magnetic wave that travels in the same direction, and they mutually propagate each other to produce an electromagnetic wave. Finally, to earn the 3rd mark, one example is a radio wave, which is used in astronomical observations. And there you go, 3 marks. Done. The ability of electromagnetic waves to travel forever is what allows us to capture the light of something so far away. It's their spectrum of frequencies that we perceive as vibrant little bursts of color. And it's their versatility in usage that makes them central to even how we communicate, and central to you being able to watch this video. Stay tuned for more content like this, and in the meantime, stay curious, stay imaginative, and never ever stop asking questions.